Okay, now we're going to show the energy levels for the molecular orbitals that are constructed from the 2p atomic orbitals. Right. So the first one we have, lowest energy, is going to be constructed from pz-pz overlap. So remember, this is going to look kind of like this. Right. And that's going to have sigma symmetry, right? Because here are our nuclei. Here's our axis that runs through the two nuclei, so our internuclear axis. We have symmetry around that, and so this is going to be 3 sigma. Okay, this is followed by the pi symmetry orbitals. Okay, 1 pi, 2 pi, right? And these are constructed, for instance, the pxy right, that are parallel to each other, and so we end up with something that looks like this for our pi symmetry. And remember, that's doubly degenerate because you can construct this out of the px-px and the py-py. Okay. So, and then we have the corresponding antibonding orbitals. Okay. So the next in the energy level will be the corresponding pi star, doubly degenerate. And then finally, our 4 sigma star, which is generated from destructive interference or antibonding overlap of the 2pz orbitals. Okay, and so what we end up with here, right, is our energy level diagram for each of these oxygen atoms contributes. Right, you have 2 electrons in the 1s2, 2 electrons in the 2s2, and then 1, 2, 3, 4 in each of the p orbitals, or in the p orbital manifold. Okay, and so we have for the 1s orbitals, so for the MOs constructed from here, we have 4 total electrons. So we fill the MOs that are constructed from there. Okay, we have another 4, 2, 3, 4. Okay, and then we have a total of 8 electrons for the remainder. 1, 2, 3, 4, 5, 6. All right, and then we're following our off-bow principle and Hund's rule, right, and Pauli exclusion principle, and what we end up with is the final electron configuration, where we have 2 unpaired electrons in pi antibonding orbitals for dioxygen. Okay, and so what this indicates, right, is that we have unpaired electrons, and therefore this should display a spin. So this is 2 times 1/2. Our spin is going to be equal to 2 times 1/2 equals 1. Okay, and that's consistent with the paramagnetism of dioxygen, right? And so this is one of these interesting things that can be explained by molecular orbital theory that can't be explained, for instance, if we draw a Lewis dot structure for dioxygen, right, where this can't explain, for instance, why there's paramagnetism, because this can't show explicitly that there's unpaired electrons for dioxygen. So this is showing that, but since we have the other thing we can explain, though, just as well using molecular orbital theory versus looking at the Lewis structure, right, is the bond order, right? So remember, the bond order will be the total number of bonding electrons minus the total number of antibonding electrons divided by 2. And so we can do that. Or in bonding orbitals, we have 2, 4, 6, 8, 10. So our bond order is going to be equal to 10 minus the number of antibonding electrons, which is 2, 4, 6. So that's going to be equal to 2. And so the bond order suggests that we should have a double bond in there, and that's consistent with what we get for the Lewis dot structure for dioxygen as well.